Hello and welcome to another episode of Deep Dive into Applied Science. Today we are talking about lasers, holograms and a very interesting topic called shearography. And our guest will tell us a bit more, and our guest can introduce herself.
Thank you. My name is Jessica Plaßmann and I am a PhD student here at Trier University of Applied Science, and I'm in the engineering department and I am working with lasers.
So before we dive deeper, please describe your whole PhD project in one sentence.
Okay, so I am trying to find out if anything like an object, any material will break without actually having to break it. And I try to find that out with a very specific method, which is called shearography or holography. Those are like basically two different methods. And I am trying to...
So you basically try to find out when things will break without actually breaking them.
Yes.
So what exactly is shearography and how does it work? Maybe you can tell us a bit more about it.
So shearography is a non-destructive testing method which works optically. So we are using laser light, which is widened and that illuminates the surface of an object. And with the speckle effect that will appear on the surface, we get somehow the fingerprint of this surface, and then we can take one image of one loading state, which will be non-loaded. And then we load the material a little bit by maybe like illuminating it with a halogenic lamp, which is like heating it a little bit. And then we take a second picture, and by the difference of both images will be my deformation, or in the case of shearography, my deformation gradient, which will then allow me to find out if there's any anomaly on my material that is excited by the loading method I chose.
So you mentioned that this method of testing is non-destructive. So other methods of testing destruct the things they test?
It is about material characterization, and in a lot of times we want to find out how much my material can take. So a lot of tests are like tensile testing, where I take the probe and I just I pull until it cracks. And then by the look of the crack, I can see if it is more of a stiff material or anything like that. But in this case, my material is broken. In other cases, like in a production line, you cannot test everything to prove that the part will hold, like that the part will do what it is to be, like what it should do. And so in a lot of times, they just take like some like small amount out of this production line, and then they will test those. And if they all were good enough, like if the material properties were the ones we expected, one can say that every other part also will work, but that's some statistics thing. Basically, one does not know if there is any part inside of this line that may not be as good as it should be. Therefore, non-destructive testing is on the rise, so there are a lot of different methods, but I'm focusing on one specific method because like thermography is non-destructive, ultrasonic methods are there, but it is very hard to look into the material without like cutting it open.
Mm-hmm, mm-hmm. So which focus do you have exactly? You already mentioned that you focus on a very specific field.
I am focusing on the optical methods, which work with laser light in the visible spectrum. And we are working like specifically with the digital speckle pattern interferometry, which is what I call holography, and the digital speckle pattern sharing interferometry, which is shearography. But I will only use the shorter words because it's easier to understand them.
So you mentioned the speckle effect. I've actually never heard of this. What exactly is this effect?
So the speckle effect that appears if we are using laser light, which has the property of being monochromatic and coherent. That means there is some kind of relationship between the waves like the light waves. And we are illuminating the surface, and the surface that has to be rough in this same, like in the laser wavelength area of roughness. So there will appear some kind of scattering on the surface, and it looks a little bit like when you see old TV screens, this like ants thing, it moves somehow. That is because it is an interferometric effect, and the interferometry will appear on your eyes. So because you cannot hold your head very still, there is some kind of movement. But if I use a camera, which is like perfectly in her position and will not move like I move when I am standing somewhere, there will be no movement seen on the surface. It is just like some grainy pattern. Some people feel a little bit sick when they look on it because it moves.
That's actually a great comparison with the old TV, because I have a clear picture in my head. But when you mentioned lasers, or that you are working with lasers, my first thought is, lasers, they probably have a very high energy consumption, or am I wrong?
The thing is, if you're using high energy lasers, it is always a safety risk. And like if you want to use a laser for wielding, for example, then one would use a laser that has a lot of power. But the lasers we use, they have basically no power. I can look at them with my eyes without hurting anything. But we use it widened. So the laser is always like a little bit more dangerous if it is focused to like one point. That is like the laser one has in mind. For us, it's just like this. It looks like just a green lamp, to be honest. But a green lamp would not work this way because it is not monochromatic.
So testing things without breaking them sounds like a very useful thing overall, but I don't know where shearography, very difficult word to pronounce, where this method is used, in which fields. Maybe you can help me out.
It is not used that much. That is why I'm researching on it. The thing is, it is quite an old method. So like it is like maybe like the first time it was mentioned is in the 70s maybe, but back then, lasers were very expensive. Cameras were expensive or did not exist in the way they do today. And therefore, people did not use it. So it has not like spread very widely. People use it in very narrow, like niche areas like aerospace engineering. When you have like, you can use it when you have very complex parts. And very like hybrid materials and stuff. It has its advantages. You can use it where other methods fail, but it comes at the cost of being like a little bit more complex.
But also sounds like it's on the rise, because I don't think aerospace engineering is that kind of small niche. So is shearography getting more popular, or is it still like a very small testing method?
I have the feeling that it is getting more popular right now. There are a lot of papers that are coming out. There are, like when we used to go to some congresses or anything, the shearography part was always like we were listed as others and stuff. And there was not a shearography session or anything. But now we've seen that in a bigger congress in Europe, they have even a shearography session. So I think it's on the rise right now. So people have finally understood that this is a very good method.
It also sounds, well, correct me if I'm wrong, it also sounds like a very sustainable method for industries. Like you don't have to break stuff.
Yeah, like it is sustainable in this way. Like the thing is, industry does not break a lot of things. Like if I have like thousands of parts and I take 10 out of it and break them, those 10 don't make this big of a thing. But what makes it sustainable is that I could go for parts that have like a guarantee, and we say, okay, this part should last 5 years, and after the 5 years because of security, we would like throw it away. But we can examine this part with shearography and see if it could last any longer, maybe. And we're going for this thing that is called the 100% control, that is safer for like especially regarding any parts that have to do with humans or anything, like maybe even parts that are used inside of humans for like medical devices. One would think that every part would be tested and that every part is working, but a lot of times it is not the case. But if we could test every part before using it,
Can you test every kind of material? For example, I don't know, this table, this laptop, this cup. Can you test everything?
Basically, we are mostly material independent. So we can test any material that it has this optically rough surface. Transparency can be a little bit challenging, but where shearography has its advantages is, for example, for honeycomb structures or like fiber-induced resins, where the established methods have trouble finding defects or anomalies, because they have trouble with this, like more than one material in one. Like not every method has this trouble. So every method has their niche, has their advantages, has their disadvantages. But this is specifically something where shearography or holography can be used.
If you look back at your whole PhD project so far, what has been the biggest challenge?
I think the biggest challenge, like there are several that maybe a lot of PhD students also know very well, which is funding and getting the resources you need, because I need parts, I need cameras, I need lasers, and it's all like someone has to pay that. So it's a lot about writing stuff to get money to buy the stuff you need, because I cannot just like research something online and then write my paper, because I have to do real experiments and develop stuff. And therefore I, of course, need parts, materials, everything. And another thing, like specifically for the part of non-destructive testing research, is that I have to find the field of use for my method. And when I then go to the company and say, can you please give me all the faulty parts you have? Then the company will say, we do not have faulty parts. Of course not.
What else should they say?
And yeah, what else should they say? And because like I'm a researcher and I need to publish stuff. So I would be going like, look at this company. They have this faulty parts and now we can find the defects. But as long as the company has its method and finds faults on their parts, the faults they need to find, and I come to them and say, yeah, but we can find more faults with our method, the wish on using this method in the company can be not that big.
We can make you safer. We can make you more sustainable.
Yeah, I know that is the reason I'm doing this, but it's very hard to get to the parts and to get the information of the companies, because they are always a little bit scared of like publishing stuff. And it's also, it is costly for them.
Do you work alone? Do you have like a small team, or how does it work exactly?
So currently in the laboratory, we are several people, 2 PhD students, and we have some students from the master's program in our department that work with us, because like I have a funding of a which is called SIM, and with this we can also have like we can pay students to work with us, and so in this I have 2 students that work with me on this specific project, which is about holography. And the other PhD student is also working more with shearography, and I'm doing like things that one can do for both, basically, because I'm more about the automation of these methods. And yeah.
So you mentioned the financing by SIM. How does your funding work? How looks the financial aspect?
So actually, when I started my PhD, I was funded by a scholarship of Nikolaus Koch Stiftung here in Trier. They specifically grant those scholarships to PhD students at this university. But there was this thing, because I need the materials, I need the stuff, and this scholarship is just like for the person, for the work of the person working on their PhD. So I worked on a research proposal, and that is for this SIM project, which is basically a project that is for smaller or medium-sized companies or universities to work on projects like we do. We have this patented device, which is called microferroscope, which has holography, but inside a microscope. So it has both, like, we try to get the advantages of both methods on using holography on a very small scale. And that is where we got granted this project funding. And that is how we can pay myself and my 2 student colleagues.
Sounds like a PhD project which is very heavily dependent on materials and resources where you can test on.
Yes.
So
yes.
That's probably the most, financially challenging aspect.
Yes.
Okay. So there are probably some people watching or maybe even listening that are also thinking about doing a PhD in the future. What can you tell them? How do they have to prepare?
I would say one has to know that they are about to have, like, it sounds bad when I say it like that, but it can be frustrating at the beginning. And you have to be very sure that you want to do this. And if you are sure, then go for it. The first thing to check is always the funding. I know there are departments that need less funding or more, but like even if you're not in a very experimenty department like I am, you need funding, or like you need a lot of money for publications and anything. So that should be a thing to keep in mind for everyone that wants to do a PhD. And otherwise, if you are able to like keep being interested in a topic and going very deep into it, then just go for it.
That actually sounds quite good. So how can people, or maybe even industries that are interested in you and your work, how can they contact you?
One can contact me via LinkedIn. I have a profile there, and my email address from the university, which is plaßmann@hochschule-trier.de. That is, like, maybe we can like show it, because it's hard to know how it's written, because the university does stuff to our names to prepare those mail addresses.
We will work it out.
And otherwise, I think one can find me or my even like publications via Google. Yeah.
Perfect. That sounds actually great. So thank you very much for coming on Deep Dive.
Thank you for having me.
Explaining your very interesting topic. Actually, in the beginning, I thought it's going to be more complex, but you did a very good job in explaining it. So thank you very much. And also thank you for watching, maybe even for listening. And we will see and hear each other on the next episode of Deep Dive into Applied Science.